Before doing these FE exam practice problems, let's say those covering statics, dynamics, mechanics of materials, structural, and really the majority of these FE exam topics, we need to be comfortable with force vectors. And this is exactly what we're going to learn today. So what I want you to do, get a blank sheet of paper, take your own notes. So build your own notes, draw diagrams, engage your active learning as we cover force vectors. 2D force vectors. So let's say we have a force magnitude in 2D. 2D meaning it's only in the x direction and y direction. X direction we denote as the I component, and y direction we denote as the j component. So we know, let's say we have a force, and a force, we know it's a vector. It acts like a vector, and that's the one shown in red here. And it's actually angled. So a vector here will have a direction and a value or a magnitude. So we have a magnitude, let's say it's 500 newtons, 500 pounds, whatever it may be. That's going to be the magnitude. And the direction is actually specified by the angle in this case, something we often see when we do statics. So the angle is theta. So now we know when we do our problems or FE problems, we have to get the components of the force. So the total force is the one in red, and it's going to have two respective components. It's going to have the Fx component and the Fy component. And we do that because we know, let's say when we do force equilibrium, we sum all the forces in the x and we only take the x components. Then we sum all the forces in the y and we only sum all the forces in the y direction if we had a lot of forces for that system. So now, how do we get these? How do we get Fx and Fy? It's right here. So we know Fx, it's always the force. So the force here is like a magnitude. So we can put those two lines next to it to denote that it's a magnitude. We take the magnitude of that force and we do cosine of theta. What's Fy? Fy is the force. Let's say 500 newtons, 500 pounds that would be given. Then we do sine of the angle theta, and that angle theta would be given. So now you might be asking, cosine and sine, where does that come from? Comes from trigonometry and mainly SOHCAHTOA. SOHCAHTOA, and let me write that on the side here. So the sine is going to be the opposite over the hypotenuse, and we do ka. So the cosine, C for cosine, is adjacent over hypotenuse, and we do toa. So this is going to be the tangent, it's going to be opposite over adjacent. So this is a must know, and we do this for analytic geometry, and it comes from trig. So we know here that this Fx and Fy, so we know this Fx has cosine. Why is that? So what I want you to do here is imagine a triangle, but we have to imagine a triangle and we have to kind of translate one of these forces. We could take this Fx and move it here, then adjust the angle, put a new angle. But what we could do is take this Fy, we're allowed to move this force vector because we're not changing its magnitude. And the direction is just going up. So it's just going up in the y direction, that's fine. If we move it and translate it, we're allowed to do that for force vectors. We cannot, let's say, increase the length of the vector, that changes the magnitude. But we can translate it and move it. So what I'm going to do is take the Fy and move it here. And now when we do that, notice something. Notice Fy, Fx, and this side, and that gives me a triangle. It's a right triangle. And for right triangles, we can apply SOHCAHTOA. So now, with respect to the angle, always with respect to the angle, notice that Fy is going to be what? The opposite side, O for opposite. And here, the force magnitude, which is the one in red, would be the hypotenuse side. So here, with respect to the angle, we know we're dealing with the opposite and the hypotenuse. Which one is it? The sine. So S stands for sine. So here, our Fy component is the sine. It has to be that. But all you do is really this, right? Now let's prove Fx. Fx is going to be cosine. Why is it cosine? Notice the Fx is going to be here. And with respect to the angle, always with respect to the angle, it's going to be the adjacent side. And here we have the hypotenuse. So this is the adjacent side, and we know adjacent hypotenuse, it's going to be C for cosine. So that's why Fx and Fy are cosine and sine when the angle theta is located here. But now, let's check this out. What if the angle theta is right here? Angle theta is there. What's fx? So it says fx is f sine of theta. That's true. And fy is f cosine of theta. And notice why. What we can do is take this fx and translate it and just move it here. I'm allowed to do this. I just put fx here, just move this, put it there. We make a right triangle. So our fx is going to be what? With respect to the angle, it's actually the opposite side. This is the hypotenuse side. So opposite hypotenuse is going to be sine. So our fx component is f sine of theta, the force magnitude sine of theta. Now our fy is going to be what? Fy, with respect to the angle, this is the adjacent side, this is the hypotenuse side. So fy is f cosine of theta, because adjacent hypotenuse, we use cosine. Now, in summary, this will always work. This is a big question I get asked a lot. So if the angle theta is there, this is theta, is fx always cosine? It is not. So this is something you probably remember from statics. It is not always cosine. It depends where the angle is located. So if the angle is here, this, yes, it is. But notice in this case, the angle is located here, and fx, or x component, is actually not cosine, it's sine. But what we can remember is this. Note this down. When the angle is touching the force component and touching the total magnitude or the resultant, when it touches that force component, it's always cosine. There's no question. If you remember that, it's a lot faster than doing the SOHCAHTOA stuff. But it does come from SOHCAHTOA. Again, when the angle touches the component, notice how it's touching the fy component, and it also touches, always, it should touch the resultant or the force magnitude that we're trying to break down. When it touches that component, what's fy? Cosine. And that's what's shown here. It's f cosine of theta. If you keep that in mind, you're going to get these right when you break down these components. So now let's denote that in the handbook, in the latest FE handbook, the vector form of a force is actually given in these Cartesian coordinate systems. And all this says is you have the I component and the J component. And we can go back up here. The I component here is going to be along the X. The J component is along the Y. So this is J along the Y, I along the X. And what we will do to put it in Cartesian vector form, you just take the fx value. So we calculate the value for this, and you put it there, and you just attach an I to it. Those are your I forces. And you do the same thing for fy. You take your fy value, you calculate it, put a j next to it. And that is denoted as a Cartesian vector form. And we know that's important. Let's say when we're adding, let's say, vectors, we only add the I components together. If it's j components, only add the j. And also for 3D, the k components, only add the k. And also for, let's say, the cross product, we need those I, j, and k components, and also the dot product. So when we do these vector operations, it's really handy to keep these forces in Cartesian vector form. Now, what if the angle theta is not known? It's not given. Rather, we're dealing with small slope triangles. Or maybe even we get our own small slope triangles based on the shape of the truss, or the certain dimensions that we're given. We can get these small slope triangles as well. And we can get the angle too. So we know here for small slope triangles, it's going to be, let's say, given in a form like this. They'll probably show you a triangle next to the force. And let's say common ones is a 3, 4, 5 triangle. The 5 is going to be the longest side. So that's going to be the hypotenuse side. Another common one is a 6, 8, 10. And you don't really have to remember these. We just have to know how to break down these components to get these components. So let's say, for example, we want the fx component, the component in the x direction. We take x over r times f. Let's look at this. Let's say x is 3. Let me put 3 for x. Y, let's say, is 4. What's r? R has to be 5. This is the hypotenuse side. And you can get that r using the Pythagorean theorem. So the r value is going to be the square root. We take the 3 squared plus the 4 squared, and we get the 5. So that would be that. So you can always use that. It always works. So we know here to get the fx, we take the x value, So the 3 divided by r divided by the hypotenuse of the small slope triangle, and you multiply by the force. Or you can take the force times x over r. That's all we do. Fy, you take the y time divided by r, y divided by r times the force magnitude. That gives me my Fy component. And then again, we can put it in Cartesian vector form. Just take your Fx value in the I hat direction plus your Fy value in the j hat direction. So now, what if you're comfortable with angles? What if you prefer using angles? So some students like only using angles. We know we can actually get the angle. We can get the angle from the triangle. From the triangle, let's say this angle. So the angle is going to be there. And to get the angle, what do? It's going to be the tan rule. And that would be the tan inverse. We know tangent is going to be the opposite. The opposite side is going to be 4. Or the y value in this case, divided by the adjacent side, which is the x. And that allows us to get the angle theta. And here with that angle theta, we just have to be careful. Angle theta is here that we just determined based on this orientation. That theta would be the same as this angle theta. So that's the exact location. So our fx value would be what? We said if fx shares the angle in the magnitude of the force, it's always cosine. So it's going to be the f value, the magnitude cosine of theta. Then the fy has to be sine. So f sine of theta. So you can interchange these. So whatever you feel comfortable with, and also based on the geometry of the truss, the frame, the system we're analyzing, you can get these angles and you can also get these small slope triangles. 3D force vectors. So let's look at these. So let's say we're given this diagram, and what we're going to do is relate it to the FE handbook equations. So let's say from the latest FE handbook, we're given this fx. They say it's the f, the total force, cosine of theta x. Fy, cosine of theta y. F, cosine theta z. Fx, Fy, Fz. And we know the z is going to be introduced because we're working with 3D. In the past, it's 2D, x and y. Now we have 3D with the z. So now when they say theta x, theta y, theta z, they're referring to the angles that are measured, let's say for theta x, from the x-axis to the force. What's theta y? It's from the y-axis to the force at interest. In this case, we're focused on this force. Then Fz is going to be from the z-axis to the force. That's our theta z. So just be careful. That's what they're referring to when using those equations. Also, when we're dealing with small slope triangles in 3D, we have the x, we have the y, now we have the z direction for that triangle. So how this would look, we can visualize this for, let's say this force, the force here, we can say that we have this is going to be in what direction? So it's going up and down. So this is the z. We put a z value here. Then we know what we will do is going to be the x. So we can put that like that. And what would that be? That would be our x. And the last one would be the y. So the y has to go in the y direction. So we can visualize a triangle like this. And let's connect this and build a triangle like that. So here what we're building is going to be, this is the y, this is the x, this is the z. And that's what we're talking about here. To get fx, you take the 1 in the x, so it's going to be this distance for that triangle over r times f. Same for fy and same for fz. And here we can do that for this force. So imagine this force. How do we get that? We can get our fx to be what? There's no x. There's no x because this force is actually only in the z-y plane. So that's 0. What's our fy? Our fy is going to be the force f, and we take the y distance. So that's going to be 7 over r, the hypotenuse of the triangle, which is 25. And the last one is fz. What would that be? We take the f value, the total force magnitude, and we take the z run. So that's going to be 24 in the z direction divided by the r, which is the 25. So that's how we would do that force and break it down into its components. So it only has a j component and a k component. The I component is actually 0 for this one.